Our topic for today are trigonometric substitutions. Before we start talking about trigonometric substitutions, we want to review a few details from trigonometry. So let me work on the following question. If alpha is an angle that's between 0 and pi over 2, that means in the first quadrant, and if sine alpha equals 2/3, how much is tan alpha? Or calculate tan alpha. So one way to solve this problem is to use the fact that sine alpha equals 3/2, 2/3 probably, it's 2/3. Use arcsine function or use calculator. And get the value for alpha. So that will be using arcsine function, or sine to the -1 function. And then from alpha to calculate tan alpha. But the question is, can we shortcut this process and get tan alpha directly out of sine alpha? The answer is yes. And in order to do that, we can use trig identities, or there is a very simple way to do this using actually triangles and just definition of trigonometric functions. Good news is that our angle is in the first quadrant, so really, or at least like this. Although we know that it's not pi over 2 for this value of sine alpha, and then create a triangle that actually has these properties. So what would that be? If sine alpha is 2/3. Then from there we can recreate a triangle that actually involves such an angle alpha. There are many such triangles. If this is angle alpha, we can choose the side as large as we want, but generally we are most interested in ratio, so that's really irrelevant. Do we take small triangle or a huge triangle? The easiest way to do this is actually to read the numerator and denominator of the fraction as sides of your triangle. And according to definition, this is opposite over hypotenuse. So we put that our alpha is here, then we can just read that the opposite side is 2, hypotenuse is 3. It doesn't have to be that. It could be twice bigger, 10 times bigger, but as I mentioned, since we are interested only in ratios, we have full freedom of choosing particular values, and these are the easiest one to choose. And then what? Then one edge is missing, we can easily recover that edge using Pythagorean theorem, so we get x squared plus 2 squared is 3 squared. From here, x squared is 9 minus 4, which is 5, so x is root 5. And now we can answer any question involving trigonometric functions of this angle, among them tan alpha as well. So tan alpha is opposite over adjacent. It will be 2 over root 5 or 2 root 5 over 5. And generally this is the technique that we'll need quite often when we finish our integration process to kind of interpret the result. I'd like to squeeze in here a similar problem so that they are on the same board. Similar problem where things are a little more ambiguous. What if we said here again alpha is between 0 and pi over 2, and sine alpha is just x. So x is a real number, of course, x is the number between 0 and 1. Can we repeat the same procedure? This x and this x here have nothing to do with one another, or not much to do. So don't think that that's that same x from a minute ago. So what do we do here? We'll basically repeat the same procedure. The fact that x is unspecified, it's not 2/3, really should not bother us, so we'll think of it as x over 1. And then again, we'll create a triangle. Here's our alpha. X is again, so x over 1 is basically opposite over hypotenuse. So we read opposite to be x, hypotenuse is 1. This missing side, I cannot call it x this time, as I did a minute ago. I will call it b. Then I have what? That b squared plus x. The same, I'm doing the same work. So from here, b equals square root of 1 minus x squared. And then if I want tan alpha, then we'll have what? X over square root of 1 minus x squared. So basically, this looks more abstract, but moves are exactly the same. The only thing that's worth mentioning is one numerator and denominator were here, clearly readable. Here 1 was not transparently placed there. And then there is one more detail, and let me show you what happens if your calculation involves angle that's not in the first quadrant. Then you have to be a little more careful. And let me do that, do the same problem, this one. So let me erase this. And then to avoid repeated writing, let me just say here, change the assumption and say alpha is between pi over 2 and pi. So alpha is in the second quadrant, sine alpha is 2/3, which is consistent. Sine alpha could be 2/3 in the second quadrant. So now we want to calculate tan alpha. So what do we do there? Basically we do exactly the same thing. Although this doesn't sound right, because alpha that I used a minute ago is acute angle, and this angle is not acute angle. Here is the best way to handle this. So we will not work with alpha. Although people write alpha, if you really want to be accurate here, you can call it alpha star. That's called a reference angle. Alpha star is the reference angle. If this star confuses you, you don't have to have that extra notation. So pretend that alpha is acute angle. And then you finish all the calculation with that reference angle. It works exactly the same way as there. All the calculations work the same way. But then what? This is tan of alpha star is 2 root 5 over 5. But I didn't want tan of alpha star, it's just tan of alpha. But then tan of alpha itself is always either equal as any function of the reference angle, or you need to switch the sign. And then that's not the big deal, because if I know that alpha is in the second quadrant, then I know the second quadrant is here. Then I know what? That either I know that tan is negative, or that sine is positive and cosine is negative. So generally I just need to, absolute value is the same. You just need to do the adjustment and put an extra minus. So you finish triangle calculation the same way as before, although it's done what we say for a reference angle, and then at the end you just adjust, so adjust the sign. And you will not get in any kind of troubles if you keep that in mind. As I said, we'll do a couple of problems with integration, and then you will see how it all works. Let's start doing the problems. So using this, you will see where we'll start doing problems. And let me put all three strategies on the board. So if you get integrals, integrals involving square root of 1 minus x squared, 1 plus x squared, square root of x squared minus 1. So, if we see expressions like this, or square root, doesn't matter. So what happens here? We see square roots all the time. They look very similar, but they are dramatically different. One has a number, positive number, 1, minus a square. The other one has a plus in between. And the third one has a minus in between, but x squared comes first. And generally, a rule for the day is the following. If you see square root of 1 minus x squared, good substitution might be. These are not absolutely precise rules, but suggested substitution. Suggested substitution is x equals sine t, or sine u. Did I do u or t? I did z, doesn't matter. Why is that a reasonable substitution? You will see that from our work, but the main idea is when you plug in sine t, then 1 minus sine squared t would be cosine squared t, and then you can square root that quite nicely. So that's it, something that to help us to kind of eliminate square root. The same way here, suggested substitution would be x equals tan t. Why is that? Because 1 plus tan square of t is actually secant square of t, and again, you eliminate the square root. And the same way here, suggested x equals secant t. That's it. That's the whole lecture. Here are the three ideas, and then we'll see how they all work in a specific setting. So problem number 6. We have integral of 10x over x squared square root with 10 dx. 10 dx 25 minus x squared. So what happens here, as we mentioned, we have our buzzword. The buzzword. You can say, yes, but here we don't have 1 minus x squared. We have 25 minus x squared. Generally, I should probably generalize this. So instead of 1, I put a squared. And then you get the extra a here. And the same thing here. You get an extra a here. It's minus a squared. You get an extra a. That a is just factored out, so not a big. So now when we have a serial rule, then obviously we are here, 25 minus x squared. A squared is 25, so a is 5. So our substitution is x equals 5 sine t. And now from our calculation, you will see why is that convenient. So then we'll have that yes, we'll do dx first. So dx is 5 cosine t dt, which is convenient. And then what happened here, that's what we promised for a square root. Square root of 25 minus x squared would be square root of 25 minus 25 sine squared t. I factor out 25 times 1 minus sine squared t, and that would give us 5 times square root of cosine squared t. Be careful here, square root of 5 cosine squared t is basically just 5 absolute value of cosine t. here's one detail. We don't have to try all possible values of t, just those that can cover, because this expression exists when x is between -5 and 5. So I want enough of t's that cover everything between -5 and 5. So normally we take t to be between -π/2 and π/2. Why? Because you know how a sine wave goes. So generally, if I just take that wave between -π/2 and π/2, then it will cover all the values between -1 and 1 times 5, all the values between -5 and 5. Why is that important? Because between -π/2 and π/2, cosine is positive, so I don't really need absolute value. Maybe I here did too much fine analysis. If it confuses you, you can just be a little more relaxed about it. And now look how nicely it will all open up. 10 times dx is just 5 cosine t dt. X squared is 25 sine squared t. That square root is 5 cosine t. So what did we accomplish? And that will be the idea for the whole section. We don't have a radical anymore, but the price is the expression that has no trigonometry suddenly has trigonometry. So this is where this lecture is different from the previous one. In A3 we had trig functions to integrate. Here there are no trig functions up front, but generally you include them in order to eliminate the square root. And now we get a trig integral basically. 5 cosine t and 5 cosine t cancel each other out. 10 over 25, they go out as 2/5. 10 over 25. So it's integral. Who's left? Just 1 over sine squared t, which is cosecant squared t dt. And that's a table integral, so it all looks simple. So it's 2/5. And what would that be? Negative cotangent t, so it would be minus 2/5 cotangent t plus. Wait a minute, but we have to get back our original variable, that is x. And that's what I've been telling you in the introduction. Actually, we know how much is sine t, but we want to know how much is cotangent t. So, now our goal is to interpret this in terms of x. So switch back to x, and here's what we'll do. We know that sine t is x over 5 from here. Get 5 on the left. Sine t is x over 5, which is opposite over hypotenuse, like we did in the introduction. We draw a triangle. Here's our t, that's an angle. I label opposite to be x. Here I put 5. Then I calculate Pythagorean theorem. How did we call this guy? B. So b squared plus x squared is 25. B squared is 25 minus x squared. So b square root of 25 minus x squared. And then what? So now I can calculate how much is cotangent of t. And that would be adjacent, which is b over x. And that would be square root of 25 minus x squared over x. And I replace that, and I'm done. Minus 2/5 square root of 25 minus x squared over x plus c, and I assume that that's our result. That's good. Although there is a little tiny discussion here that I skipped. You know, it's not the end of the world if you skip it, but it's good maybe to know things accurately. Because what happened here? I did all this with the assumption that x is positive. So if x is positive, then what happens? If x is positive, your angle is in the first quadrant, so everybody's positive, I can draw a triangle, everything is good. But what if x is negative? Then what happens, our angle is actually in the fourth quadrant, so our angle is not here, our angle is here. And how will that influence the story? I know that cotangent is negative, so I might be wrong, I don't know if my sign is accurate. Cotangent should be negative, but x is negative, this is positive, sign is fine, nothing to intervene with, so everything is good. So sometimes maybe that analysis is due. All right, so that was our first problem with this idea, and then we'll keep going with a similar problems. An idea, the whole really section has this flavor. So problem number 10, it says integrate square root of x squared minus 4 over x dx. So if we follow our list of suggestions, we can obviously see that our expression on the square root looks like in the line number 3. So hopefully the substitution x equals 2 secant t should work. Because a squared is 4, so a is 2. Let's see, dx is 2 secant t tan t dt. They're just the rules for derivatives. And let's see how do we handle the square root. Square root of x squared minus 4 equals square root of 4 secant squared t minus 4, which is square root of 4 times secant squared t minus 1, which would be 2 times secant squared t minus 1, so the square roots of tangent squared t, which would be 2 times absolute value of tan t. So what do we do now? Like a minute ago, we said what? Okay, that's all good because x maybe tan t is always positive. A minute ago, when we got rid of absolute value, we had cosine is always positive, nothing to worry about. But here, if we want to be really serious about this, we have to analyze. Let's make it first easier. There are different ways. You can do t, because secant, like cosine, really to cover both positive and negative values. You know how cosine goes. Cosine goes like this. So we cannot go minus pi over 2 to pi over 2 because you're covering only positive values. You have to go from 0 to pi. And then secant as reciprocal of that also goes, here is the asymptote. So it also goes, needs, here is what this is 0, here is the asymptote, and then it recovers here. So generally, you need both 0 to pi over 2 to cover positives and pi over 2 pi to cover negatives. So generally here, t should be, I hope I'm not making this too complicated, should be between 0 and pi to cover both positive and negative values. But for a moment, I will just focus that t is between 0 and pi over 2, so that we just do machinery, and then we'll go back to see what happens in the other case when x is negative. So what would that be? Then tan is just positive, so there's nothing to worry about. So it will look like this integral. X would be 2 secant t. The square root would be 2 tan t. And dx is 2 secant t tan t dt. And then what do we do? Going to cancel. The secant and the secant cancel. This is times. So we pull 2 out, and it's integral tan squared t. And what do we do here? We can say what? That tan squared t is just secant squared t minus 1 dt, which would be integral of secant squared t is just tan t. Integral of 1 dt is t plus c squared. So what would that be? I can distribute. It will be 2 tan t minus 2t plus c. Here we have the same situation that we have secant in terms of x, and we need tan. And what do? The same business. So generally here is your t. So we know that secant t is x over 2. If you don't like that, you can say cosine t is 2 over x. X is on hypotenuse. Adjacent is 2. That missing guy, I cannot call it t anymore now because I use that as substitution. I can call it question mark. So I have what? Question mark squared plus 4 equals x squared. So question mark is square root of x squared minus 4. And then tan t would be 2 times. Tan t is sine opposite of our adjacent, so it's question mark over 2 square root of x squared minus 4 over 2. Minus 2 times here for t. To get t from here, I can either use this line or this line. Doesn't matter. Let me do arc cosine. So from here, I'll get that t is arc cosine 2 over x. So minus 2 arc cosine, or arc secant, whatever you want. Arc cosine 2 over x plus c. Let me see. Oh yes, well of course we can cancel 2 and 2 here. I hope I got it correctly done. I did arc secant plus c, and that's all good. But you remember in the beginning, just to make us a little less worried about this absolute value, I just assume that x is positive greater than 0. So that t is between 0 and pi over 2. But then, what happens if x is negative? So generally, what we can do if x is negative, we can just do the substitution and do minus, because if we need it for some definite intervals in the other case, or do the substitution x equals minus y, and then use this integral for positives that we just developed. Or we can say the following, all right? So if we want to follow what happened here, so this is now this when x is positive, where would the things change if x was negative? if x was negative, well, we must be in the second quadrant, so tan is negative. So I'll just put the reds where that changes. So in that case, we would have a minus here. Okay? And then what would, it's nicer than just carrying absolute value. That would be a little confusing. And then what would happen here, there would be a minus here. Or minus in front is better. So minus 2, that minus would be pulled out. And then what happens here, then that minus over here, you would have secant square, so minus here as well. Minus here as well, plus here. And then what would happen here when we calculate tan t, then again that minus tan t would actually, we would adjust, since tan t is negative here, and this minus would make it positive, so this expression would be correct, and then we would have here plus 2r cosine 2 over x. So if you are dealing with negative x's, although, as I said, it's much easier just if you are dealing with negative x's for definite interval, just put substitution x equals minus y. Let's continue. We'll now see the third case, how things were here. So number 16. Integral of x squared over 1 plus x squared dx. Here we don't have a square root, but generally we have little troubles with this 1 plus x squared expression because it's in denominator, so we are not sure what to do. So when that happens, one of the ideas might be to do the following, to actually use tan substitution. You can say, wait a minute, there's no square root there. Doesn't matter, this strategy could be used whether you do have square root or not. Generally, whenever you see a squared plus x squared, this might be a good strategy. Why? You'll see that in a moment. Things solidify, even whether because of square root or on their own. So we'll go what? X equals tan t. So how much is dx? Is secant squared t dt. And what? 1 plus x squared will be 1 plus tangent squared t. And that's secant squared t. So generally, what's our benefit? We lose binomials and we just go look at the things that have the form of monomial, which looks much better for algebra. So x squared would be tan squared t. This is secant squared squared, so it's secant to the 4th t. And dx is secant squared t dt. What we wanted really happened. There are no pluses, everybody's monomial. And what's even nicer, there are some nice cancellations here. So secant squared t could be cancelled with 4th power to get just secant squared. And then a little more algebra that makes it even better. 1 over secant squared is actually cosine squared, so you get what? Tan squared t times cosine squared t dt. And it gets even better because tan squared is sine squared over cosine squared. Times cosine squared t dt. You cancel and you are done in no time. So we have integral of sine squared t. What do we do there? You remember from section 3, we'll do reduction formula. So this is 1 minus cosine 2t over 2 dt. Or maybe you can do substitution, whichever way you prefer. And what would that give us? I'll rush this. Integral of 1/2 dt is just 1/2 t. Minus, and then there is linear correction, 1/4 sine 2t plus c. Here it is. All right, so, but how do we go back to the original substitution? T is easy because it's arctan, so t equals arctan x. So nothing that you can do there, so it's 1/2 arctan x. But within the trig world, you would like to express sine 2t in terms of tan t. This is even worse than a minute ago because we don't have the same angle, but that's easy because this is 1/4 times 2 sine t cosine t. So 1/4 times 2 will give you 1/2. And just we need to read sine t and cosine t the same way as we did with the triangle. So we make a triangle. So here's your t, and we know, what do we know? That tan t is x over 1. So I put x on the opposite, 1 below, opposite, adjacent. Calculate hypotenuse, square root of x squared plus 1. Pythagorean theorem. And now I can read both sine and cosine, so sine t. X over square root of x squared plus 1, and cosine t is 1 over square root of x squared plus 1. So basically what we need to do there, we arrange 1/2 just to multiply those two expressions. We get x over x, because square root of x squared plus 1 times square root is just x squared plus 1. And then what? You can say that we're a little careless again with the positive or negative sign, but this is an even function, so we can always assume that x is positive. And then, so tan t would also be in the first quadrant, so everything would work. So here we don't have any restrictions if we are dealing with positive or negative numbers. All right. More problems. Here's one problem that's a little tricky and complicated. So this is problem number 20. So to show you that even when these substitutions work, it could be a little. And I will just assume that x either equals 0 and do it just for that part of that. If I need it for negative x is to do definite integrals, I just know that this is an even function, so I can just switch to positive. So there is really no reason to calculate this for negative x. So what do we do here? So we are analyzing. Which expression reminds you of what we have out there? This one. You can say, yes, but I have an extra 2 here. We are used to have x squared. You can handle this in 2 different ways. One of them is to pull out the square root of 2 and make it then, to pull out 2 that becomes square root of 2 when it's pulled out. Or just adjust the substitution. So main thing is that these two match. So generally what you want here is you want that x root 2, or yeah, so you want Yes, you would like this to act like a square. So generally you just take that as a substitution. X root 2 equals secant. So we adjusted that root 2, because this really is x root 2 squared minus 1. So you don't have to pull it out. You actually treat it here as the whole x squared. So x squared root of 2 is secant t. And generally you will see immediately if that's a good strategy. When I square both sides, I'll get what? 2x squared is secant squared t. So 2x squared minus 1 is secant squared t minus 1, which is tan squared t works. As you see, it worked in the direction where it was designed, so we are happy that how it all goes. So it will be integral of square root of tan squared t times, we need dx. Dx, if I differentiate, I get the root 2 dx is secant t tan t dt. So I'll just, dx is then 1 over root 2. I'll pull out 1 over root 2 times secant t tan t dt. Then I don't need to worry about absolute value here because we set the x and tan, x is positive, t is in first quadrant, tan t is positive, so nothing to worry about. 1 over root 2 integral of secant t times tan squared t dt. If you remember, when we studied section 3, we said we like this to be even and we like this to be odd. Or, and this is the only unpleasant case, is when this happens. So question is, what do we do here? So how do we solve this integral here? We can actually, one of the ways to solve this is the following one. Let's trade tan square as secant square minus 1. So this will be secant t times secant square t minus 1 dt. So we get 1 over root 2 integral. I'll distribute here secant cube t dt minus integral of secant t dt. And I know that this integral of secant t is ln, it should be absolute value, but we assume that everybody is positive, of secant t plus tan t. What's that? That's in the table, so we recall from the table integral of secant t dt is ln of secant t plus tan t. So that's one of the integrals from the table. It should be memorized. So that was clean. My question is, what do I do with this integral? This integral is not easy at all. So this will now get us into bulky work. And I want to separate it out of this, so I'll call it I. I'll go on the side and do it as a separate problem, and when I'm done, I'll come back. Because I want to show that that's a little separate idea. So this is idea within idea, so probably should be done separately. All right, so how do we do this? Integral, so integral I is integral of secant cube t dt. And what would that be? We can split it as it was split. Secant t times secant squared t dt. We'll take this to be u, and we'll take this to be dv. So what would that give us? So u is secant t. dv is secant squared t dt. du is secant t, tan t, dt, we differentiate, and v is tan t. So what do we get here? We get secant t tan t minus integral of a v du, which is integral of secant t times tan squared t dt. Secant t tan t and tan squared t. And what's that? It gives us the chance for looping. This is secant t times tan could be traded for secant squared minus 1. Secant squared t minus 1. So what would that be? Secant t tan t minus secant t times secant squared t secant cubed t dt, and plus, when I distribute this minus will give me plus integral of secant t dt. And the same idea, our I appeared again. And you remember the trick? We add I to both sides, so we get 2 i's secant t tan t minus this integral, not minus, plus. This integral will already place there ln of secant t plus tan t. And then dividing by 2, we'll get our integral. So it would be 1/2 secant t tan t plus 1/2 ln, oops, we have a short space, secant t plus tan t and minus ln. And these two are alike. That's good news that I can combine them. So we get 1 over. When we combine 1/2 minus the whole thing is minus 1/2. We pull out 1/2. So we get 1 over 2 root 2 secant t tan t minus ln secant t plus tan t and plus c. Here it is. We are almost done. What's missing? We just need to do the replacement. Secant is easy, and then tan. I can also use identity. The tan t, I don't even need to call triangles. It's square root of secant squared t minus 1, which would be square root of 2x squared minus 1. And now we can replace everybody. 1 over 2 root 2. It's x root 2 for secant, and square root of 2x squared minus 1 for tangent. Minus ln, there's no absolute value because we assume everybody positive, x root 2 plus square root of 2x squared minus 1, close parentheses, plus c. And then it might be a good idea maybe to distribute this, so at least to get rid of this root 2 here. So we get 1/2 x square root of 2x squared minus 1 minus 1 over 2 root 2 ln x root 2 plus square root of 2x squared minus 1 plus c. Let me check. There are tons of calculations. If we have all our pluses and minuses in check. 1/2 x squared minus ln, wow, looks great. Looks great. And you can see the comment at the end of the problem that I did in the notes, and that was that this problem is not a reasonable candidate for the exam. So this is just for illustration purposes. You know, it's a robust problem. It really involves two problems. Problem to get J or I, that's how you read it. So that was integration by parts, and then this trig substitution that we are learning today. I'll skip problem number 30 because it's very similar to the other problems. You can see it in the notes. Of course, if you have questions, I'll gladly answer them. The next problem involves a little slightly different approach, slightly different. Actually, you already saw that in Calc 1 when you need to complete the square. And in our introduction in 8.1. So it's integral x plus 1 square root of x squared plus 2x plus 2 dx. And generally what happens here, we always talk here about the expression that involve x squared and a squared. There is no middle term, but you're experienced calculus students, so by now you know that we handle that usually by completing the square. So generally, how do we do that? We do it on the side, x squared plus 2x plus 2 equals. Then you remember, we take this number 2, we split it evenly, half, 1, 1, and then we multiply, it is 1. So generally what it tells you is that I don't need 2 here, I just need 1, and there is 1 that's extra. And then we read this using this number here as x plus 1 squared plus 1. Of course, you might be thinking, why am I showing you this triviality? You all know it. Doesn't matter then, sorry. X plus 1 square root of x plus 1 squared plus 1 dx. So basically what it says here, do the same thing with x plus 1 that you would do with x, with that middle substitution. If you want, if you are hesitant to do that, you can do x plus 1 equals u first, but there's no need. So generally what you do here is, you just take substitution that x plus 1 equals 10t. And then this expression, like we suggested before, becomes square root of x plus 1 squared plus 1. I'm going to make this a little wider. Becomes square root of 10 squared t plus 1, which is absolute value of secant t. Let me now really carry absolute value to see where will that get us. So this is absolute value of, because 10 squared plus 1 is secant squared is absolute value of secant t. When we differentiate, we get dx is secant squared t. So all looks promising. So our integral now becomes integral x plus 1 is treated as 10t. This is treated as absolute value of secant t. This is treated as secant squared t dt. And that's it. So now what happens here? It is integral. Tan is sine over cosine. So we'll get sine x or sine x over cosine, or sine x over cosine x time absolute value of 1 over cosine x, and times cosine square x. Not xt, sorry. I forgot what our variable is, so it's t. Cosine squared t dt. So what would that be? Equals. I'm a little bit kind of disturbed by this absolute value that we need to carry all the time. So generally, again, we can say, oh, let me do it just for the situation when x is positive, where actually t is positive. So when x plus 1 is greater or equal to 0, and then t is in the first quadrant. Or if we also, what if it's negative, and then if we have it in the second quadrant, then our t is negative. So in this case, as I said, if this doesn't confuse you, then we'll say plus or minus. So if t is positive, it's positive. If t is negative, it's negative. And then integral of sine t over, then we would have cosine t and cosine t, and here we would have what? Cosine squared t. Oops, 1 over. Secant square, I traded wrongly, sorry. It's 1 over cosine. Oh, times 1 over cosine squared t. And then that would be, what do we do here? Obviously, substitution is u equals cosine t. And then du is minus sine t. So what would that give you? I'll keep that plus or minus, then I'll deal with it. So it would be integral. Sine t dt is packaged, so it will be minus du over u to the 4. Now we can write this plus or minus integral. What would that be? It would be u to the negative 3 over negative 3, so it will give us 1 over 3 cubed plus. So what would that be? Plus or minus 1/3 times, what does u stand for? Cosine, so 1 over cosine cubed t plus c plus or minus 1/3 times 1 over cosine is secant cubed t plus. And then what is secant cubed? Actually, secant stands, you see here, basically now I can eat this plus or minus into, so I can say the following: 1/3 times secant squared t times the absolute value of secant t plus c, and then what do? It's 1/3 secant squared t from here, this line. It's actually this expression x squared plus 2x plus 2 times square root of x squared plus 2x plus 2 to make it absolute value plus c. And here is the result. Of course, you can write this as to the 3/2. A little nicer, but I wanted to show you how we spend that plus or minus, and that's fine. I must admit that this is a little incorrect writing. Why? Because you are saying, when you write usually mathematics plus minus means it could be both. It cannot be both. In some cases it's one, in some cases it's another. The proper way to write this is, it says, if t is positive I'll take plus, if t is negative I'll take minus. That's called signum of t. So signum of t is just 1 if t is positive, negative, and that's a standard mathematical function. I think you saw it earlier. So this would now be a nice writing. Signum of t times this, and then signum of t gets into absolute value, and that's it. As I said, I can feel already when I kind of try to handle that those absolute values might bother you somewhat, and how I'm handling it, because otherwise we'll do some cases or something like that. So let's say that I'll be absolutely happy if you can do just the positive cases, And you know, I won't take points off for not doing these little details. I'm showing them for absolute completeness, but I don't want you now to be distracted by that and miss the main line of our course. All right, and there are more problems. So actually, there are two more to do, because you know, we're not trying to pile up a new million problems, but just I hope you feel that each problem brings a different idea. And if I don't show it, I don't know how will you come up with this. So problem number 42. It's a problem like this: integral x sine of x. Generally, what I did in the notes is the following. I decided to get rid of arc sine of x. And how do you get rid of arc sine of x? Because what you know, this is so what is arc sine of x? We will be reviewing from calculus 1. When you define arc sine of x, what does it do? Arc sine of x is the function, and it maps basically, it takes interval between -1 and 1 and maps it into the interval -pi over 2 pi over 2. So it takes a number between -1 and 1 as a ratio. So take ratio as input and recovers the angle. But then what we can do is we can just give that a name and call it Z or U. U is arc sine of x. And why does that make sense? Because it's nicely solvable for x. So U is the angle, x is the ratio. So you can also say it the other way around: sine of U equals x, because they're the same thing. I'm the angle whose ratio is x, or just a ratio of that angle is x. It's the same thing to say. And then what? Now I don't need derivative ready. I can differentiate cosine U du is dx. I decided to do the same way as in the notes. So what happens there then? Then we'll have the following integral: x is sine U, arc sine x is just U, and dx is also times sine U. No, sorry, cosine U. I don't know, it's cosine U. So once again, x was replaced with sine U, as it says, arc sine x is U, and dx is cosine U du. And then what do we do here? You see, we have trig functions, and we have U, so it looks like integration by parts. Unfortunately, there are 3 of them, but generally, now I have a little trouble. Uh-oh. You know what? Let me change my mind and change the name here. Not call it U, call it Z, and we'll see in a moment why. Doesn't change our calculation. Because the reason why I changed my mind is that now I need to call someone U and V. There's a kind of reserved letters for integration by parts, and this variable was already called U, so that would confuse us. So here it is. So U equals Z, and dV is sine Z cosine Z dZ. So I might have a little troubles integrating this, but my benefit is clear because du is just dz, U disappears. And what is a V? Now I need a little integration. Sine Z cosine Z dz. Within this, so just to start the problem, I need a little substitution here. So if I call this sine Z, if I call it V, I cannot use E. We call it P. then this is obviously dt. So I don't want to write too much. So integral of t dt is 1/2 t squared, so generally it's just 1/2 sine squared t. And then everything works quite well. So when you multiply, you get 1/2 z sine squared z minus integral of a v du, which is 1/2 sine squared z dc. And then you can do to this guy whatever you want. Probably just reduction is the best thing. 1/2 z sine squared z. This is sine squared z, remember. Is 1 minus cosine 2z over 2. Am I too far here? Probably yes. I better stop recording to check. All right, looks good. So then it will be 1/4 integral of 1 minus cosine 2z. Because this is 1 minus cosine 2z over 2. I pulled out that. dc. So we're almost there. 1/2 z sine squared z minus 1/4. Integral of 1 is just z. Integral of cosine 2z is 1/2 sine 2z with linear corrections plus c. So that would be 1/2 z sine squared z minus 1/4 z and plus 1. You know what? Let me just, okay, 1/8 sine 2z plus c. And now I need to trade back, and that trade goes like this. 1/2 z would be 1/2. But sine z is x, so sine squared z, this is x squared, so this is 1/2 x squared arc sine x minus 1/4 z, 1/4 arc sine x, and plus 1/8 times, what is this, 2 sine z cosine z. So that would give us, I can factor out arc sine x if you want here, so it will be 1/2 x squared minus 1/4 arc sine x plus 1/4, right? Sine z is just x, and cosine z is square root of 1 minus x squared plus c. What did I do here? I know that sine squared plus cosine squared is 1, or I can do triangle either way. So what I use here is sine squared z plus cosine squared z is 1. So generally, since sine z is x, then what? So cosine z, cosine squared z, sine squared z, so x squared plus cosine squared z is 1, so cosine z from here is square root of 1 minus x squared. I just disregarded again that other case where it's negative, so it's just square root of 1 minus x squared. Let me check if my notes agree with this calculation. Minus 1/4 plus 1/2 plus 1/4 looks good. All right, one more problem. Oh, well, actually, there are 2 problems in the notes, and they are probably both worth doing. So we'll do 2 more. Sorry, I know it's only 1. So, number 44. An integral between x squared and square root of 2x minus x squared dx. It's the same story from a minute ago. We need to complete the square. So Be careful here, completing the square is a little more complicated. I hope not a big deal for you. 2x minus x squared, you pull out minus to get x squared minus 2x. X squared always needs to have 1 in front of it. And then we add and subtract, within parentheses, add and subtract 1, which is a legal move. Then this is square of a binomial, x minus 1 squared minus 1. And now I distribute back my minus. So this is right x, which is what we like a lot. So this would be integral x squared over square root of 1 minus x minus 1 squared dx. Now it looks much better. So what do? The same as what suggestion is in the line number 1, although not for x, but for x minus 1, doesn't matter. X minus 1 is sine t, dx is cosine t dt. So what do we get all together on the bottom? We get square root of 1 minus sine squared t, which is, let's write with absolute value of cosine t. No, because I don't need absolute value here. Why not? Because here that's fine. Sine t, t is between negative and some. The cosine is very convenient for that. So t goes between negative pi over 2 and pi over 2. We are happy with that because it covers all the possible values. And then cosine is always positive. There's nothing to worry about. So what would that be? It's integral. This is cosine t on the bottom. Cosine t dt. And then I have x, but that's easy. X is just 1 plus sine t. So that's 1 plus sine t squared. And this is now really routine because good news is cosine t cancel. Look how good benefit we have. Not only that we got rid of the square root, we also got rid of the fractions. And then what do? Here we FOIL this, so we get 1 plus 2 sine t plus sine squared t everything dt. And then we already saw this trick. We'll do reduction. So it will be 1 plus 2 sine t plus. This is 1 minus cosine t over 2, or 1/2 minus 1/2 cosine 2t. I just multiply immediately, distribute it so that I can combine the like terms. So what would it be? Integral of 3/2 dt, 1/2, plus integral of 2 sine t dt, and minus 1/2 integral of cosine 2t dt. Here I pulled out minus 1/2, so I thought I would put plus and minus in there. And that's it. Now we get 3/2 t minus 2 cosine t. And what would that be? Minus 1/4 sine 2t. And then what? So this would be 3/2. What is t? I need t from here, so to solve for that, t is actually just take arc sine. So arc sine of x minus 1 is t. So this will be 3/2 arc sine of x minus 1 minus 2 times, how much is cosine t? If you know sine, so do I have it somewhere? Oh yeah, here it is. Square root of 1 minus sine squared. So that would be square root of 1 minus x minus 1 squared. And minus the same story, sine 2t, that's 2 sine t cosine t. Like a minute ago we had that. 2 over 4 is half. Sine t is just sine t is x minus 1. And times square root of 1 minus x minus 1 squared. 0 plus c, we are done. And then maybe a little polishing if you want. We get 3/2 arc sine x minus 1 minus the square root could be pulled out. And look, they both have minus in front. Square root, by the way, that square root we obtained from 2x minus x squared, so it's nicer if I go back now to the same. So that's 2x minus x squared. So who's left? 2 from first guy, and plus 1/2 x minus 1/2 plus. Of course, you can now combine these two guys, but this is not good enough. Let's see what it says here. 3/2 arc sine. Yeah, I didn't pull that out. I just left it like this, but I have here opposite side. And let me see why. Oops, I made error in my notes. Actually, I traded sine squared z for 1 plus cosine 2z. No, this is correct, actually. Please correct that in the notes. All right, one more problem. I know it's a long day today. Just to address definite integrals, how do they behave? Yes, here when you address definite integrals, you really have to be careful about your input. Is it positive, negative, and all that we will be disregarded today. It's integral 0 to root 3 over 2, 1 over 1 minus t squared to 5/2. What do we do here? Obviously the same thing that we did all day long. That's line number 1. So t equals sine x. Usually we replace x as sine t, and here t was there, so we use x as angle. So what would that be? Then 1 minus t squared is actually what? 1 minus sine squared is cosine squared x. Since t is positive, we know that our x is between 0 and pi over 2, because if it had negative, I would take fourth quadrant. Here we just take first quadrant, so that's our angle x is somewhere here. So that's angle x. So we are quite comfortable that cosine x is positive and all that. So what would that be? This is 1 minus t squared to 5/2. It's just cosine to the 5th x. Cosine squared to 5/2, cosine to the 5th x. And that's it. Oh, we need dt. dt is cosine x dx. What else do we need? We need to adjust the limits. So when t is 0, we get 0 equals sine x. So x is 0. When t is root 3 over 2, if sine x is root 3 over 2, x is pi over 3. So our integral goes now from 0 to pi over 3. And so what do we get here? 1 over cosine to the 5th x. Times cosine x dx. So what happens here? This would be integral from 0 to pi over 3, 1 over cosine to the 5th, or that's a secant, so that's secant to the 4th x dx. All right. We established something here. So what was all this work? what did all this work give us? We don't have fractions, we don't have radicals, prices, we have trigonometry. And then I hope you remember this from section 3. What do we do here? So secant is to the even power, and that's good because that's source of tan substitution. So what would that be? We'll go secant square x dx, which is 0 to pi over 3. And that gives us the chance to do substitution. U equals 10x, because that's a derivative. So du is secant square x dx. Now again, change of variables. I also need secant square x, but secant square x is tan square x plus 1, which is u square plus 1. So let me postpone the limits. So this would be integral u square plus 1 du cannot be better. Just adjust the limits. Tan of 0 is 0 for you. Tan of pi over 3 is root 3. So here's tan pi over 3 is root 3. And that's it. So this would be u cubed over 3 plus u between 0 and root 3. Of course, if I plug in 0, I get nothing. So when I plug in root 3, I get the root 3 cubed over 3 plus root 3. Root 3 squared is 3, so it would be root 3 squared. That's root 3 over 3 plus root 3, but this is the same thing. So we get 2 root 3. And that's where we finish the day.